Yeah. But,
All right.
All right. Anyway, why don't you get started?
Yeah. Yeah. Okay. So here comes the bad part, right? So far I was very elementary, and now what I want to try is show a little bit of a more not at all in depth, but some of the more recent ideas there. And so I picked three, which also cover a very interesting type of description of the many particle system. And let me start with the modulated energy. So this was introduced by Serfati and her student Misia. So I hope I'm not misspelling his name. And there's a lot of more recent results that I'm really not going to go over. Also by Sylvia, of course, with Nguyen and one of her postdoc, Rosenzweig. But here I'm basically going to introduce the basic idea of the method. So this works very well for first order systems, so not kinetic system. And they've recently adapted it to cover some diffusion, but the method really works best without any sort of diffusion. So I'm going to look at this system. And here I'm going to take a gradient flow. So I'm going to take K equal minus gradient phi of X. With phi of X, something which has a simple polynomial behavior. Now, this can be extended a little bit, and I'll say a word on that, but okay. So the idea here is very simple. There is an energy, right? The system has an energy. And so let's try to use this energy to compare the discrete system with the limit. Now, in order to do that, the simplest is to introduce the empirical measure. Which I'm going to denote by mu n. And which is just a rescale counting measure. All right, so mu n of a set that just gives you the proportion of the number of particles that belong to the set. Right? And the empirical measure is a very popular object to study mean field limits. It's a little bit more statistical than just the just each individual trajectory, but it still sees trajectories reasonably well. And formally, it satisfies a limit. when you don't have a diffusion. Right, so formally mu_n solves this. Right. Provided, and this can be rigorous if you correct to make sure you don't have a self-interaction, because otherwise the product of mu_n by the convolution of mu_n with k will blow up, right? So, but if you forcefully put in the system the definition that k of 0 is 0, right? K is not continuous at the origin because it's singular. Phi can already be singular, right? But if you forcefully put it, then this is actually rigorous as long as the dynamics exist. So this is very nice. Then you define the modulated energy. Which I'm going to call En. And this is the double integral of, let's put the 1/2, phi of x minus y, and then mu_n dx minus f dx, right? So that's the limit, times mu_n dy minus fy dy, right? And this is obviously a tensorization of mu_n minus f, so very often I will just write this in the following manner. All right. So this is the basic idea, and it makes a lot of sense, right? Unfortunately, it also doesn't work if you write it like that. The reason it doesn't work is because since phi has a singularity, right? Well, you end up having the same problem here, which is the term mu_n dx, mu_n dy, when you apply it to phi of x minus y, right? You are going to hit one of the each Dirac mass twice, right? I mean, with a small coefficient in front of it, right? With 1/n. But you're still going to hit them twice, and then this would be plus infinity if you write it as is. So what you have to do here to get a correct definition is you have to remove the diagonal. And then you're going to try to get a Gromboll estimate. Right? d/dt of En of t is less or equal than some constant times En of t. And that actually works in plenty of cases, and in plenty of singular cases, and much more singular cases than what we could handle so far. So it works for Poisson. But you can actually go up to any k. Again, I'm considering only polynomial k, so those are sometimes called risk cases. Any k that is actually integrable. Right. So if phi is like 1/x to the theta, right? K is like 1/x to the theta plus 1. So you can actually go up to theta strictly less than the dimension minus 1. And this was the first case ever when this happened. But as you will see when I try to explain how this is working, you need repulsive interaction. So this is something that has zero chance of working for the Keller-Zegel system, for example. Now, here I considered gradient flow. Serfati is also capable of considering flows where the energy is preserved, right? So instead of gradient in dimension 2, I could have gradient orthogonal, for example. And then it works quite well again. And that's how they get results on to the Euler, for example. But again, here I'm going to focus on the gradient flow. Now, the actual proof is much too intricate for me to present here, especially because I want to present more than just that. So let's look at this on the limiting equation directly. Right. So let's consider two solutions F and G to the mean field limit, right? And calculate the time derivative, right, of the modulated energy, but now without an n because we're internally at the limit, which is a little bit simpler because now phi, I don't need to remove the diagonal. Now, phi is even, so I only need to differentiate one of those, right? So you see that the way this is going is relatively simple. DTF minus DTG, right? Let's take it in X. And then F minus G in Y. So that this is really just phi convolved with F minus G against DTF minus DTG. Right. And of course, I can use the equation immediately. And I have divergence X of KFF minus KG. I'm going to integrate by part, right? That's going to give me gradient of phi, which is minus K, which is minus, yeah. So, right, so I'm going to have a term like that. All right. So what we really have here is a sort of commutator. And we have a commutator because you see that right, if I had only one term, this would have a sign, right? So we want to exploit this as much as we can. And I can play with this and the kind of formula that you end up having after, you know, symmetrizing as much as you can and putting all all the terms away that you can put away, right? And it is something like this. So keep that. And then I will have something like that. Sorry. All right. And you have to work with this. And again, you have to get a Rombel estimate out of that. Now, the first point to note is that E, this modulated energy, is coercive. And that's because for the choice of phi that I made, phi hat, the Fourier transform is strictly positive. Right? So this integral is actually a positive quadratic form on f minus g. Right. So it gives an actual norm that we can use. Now, for En, of course, you have a big issue here because you have to exclude the diagonal, and if you exclude the diagonal before you transform, well, that's not strictly positive anymore. So when you exclude the diagonal, this is not a positive quadratic form anymore. And there's a lot of work to show that the defect, right? So the potential negative part actually vanishes asymptotically with N. The second point is if F is smooth, right? Then this inner product, right, kx minus y times the difference, this has the same singularity as phi. Because k has an additional singularity, but f is smooth, so the convolution is smooth, so the difference, you get an extra x minus y. It's x minus y. So there's actually quite a bit of work, again, to do on this commutator to show that indeed it can be dominated by the actual modulated energy. Sorry. There's a few ways of doing this. The initial idea by Sylvia was actually to use an extension method from Luis and Caffarelli that was allowing to treat all Reese potential. With Didier, we actually showed that you can also do that in Fourier, and then you have more general. You don't need to be as specific on K as that. And recently, with Nguyen and Rosenberg, again, Sylvia had one way of doing this that is completely in the real variable. But there's a bit of work, right? Because this pointwise domination by the kernel is not enough to do to prove this inequality between the integrals. Again, here this is an inequality on quadratic form. It is not, and this does not follow from a pointwise comparison of the kernel. The f minus g doesn't have a sign. And once you've done all of this, then you nicely propagate. Then you are done. And what you have here is already a weak strong uniqueness property. The limit. Because you need that F be smooth, right? But G can be anything. Well, anything for which the initial energy is finite, right? So as long as E0 is finite. Okay. So this is a very natural idea. Again, you still have a lot of papers around that. So, so this is going to keep on being useful for a lot of the systems. The big limitation, if you look at what it does, is, so one, repulsive, right? Because you need this coercivity one way or another. And that's here. And second, first order system, because if the system is not first order, then this type of inequality here is simply not going to be true. But first order refers to the system at the limit. So for example, there is a derivation from point charges of the monokinetic limit directly of the Vlasov equation. All right. The second type of method that I want to talk about very fast, because I've actually talked a lot about those in the past. So, is the use of relative entropy. And so this is a very, very different idea, and it consists in looking at the joint law of a system. Right, so let's call that Fn. Right. Which is something like this. And that solves a Liouville or Kolmogorov equation. Right, which is a linear equation, but it's a linear equation in very large dimension. And so in general, for my original system, it will look like this. And the question is, now again, this is a linear advection diffusion equation. Which kind of norm can we propagate on that? And which kind of natural quantity do we have that we could use to compare with the limit? So what's the limit, by the way? Well, the limit, if we believe in propagation of chaos, right, should be the tensorized version of F, right? Which you can write like this. This is actually a fun question already. Because it turns out there are very, very, very few quantities that you can even try to use to do something like that. Now, let me assume here that K is divergence free, right, for simplicity. Now, the Liouville equation, right, L, propagates all LP norm. But none of them, not one of them is useful. Well, first of all, right, if P is strictly larger than 1, sorry, they behave very badly, right? Because Fn in LP, even the initial condition, right, behaves like some constant to the power n, right? Actually, even the limit, right, so F tensorized n times, right, LP behaves like constant to the power n. So this is very, very hard to use. Okay, but what about the L1 norm? Well, the problem with the L1 norm is even initially it's probably not that great. And a simple way to see that is now to compare initially two tensorized objects, right? How is this behaving? Well, in general, unless you're lucky and there's a very specific structure between F and G, the best thing you can do here is very unfortunate. And this factor n in front of everything is just killing you. So that means that even if I was good, right? So I got a G that is a reasonably good approximation of F in L1. And then I'm trying to compare the tensorized version of both of them. It's not going to work because this is very unstable with this additional factor n. The one good object I know is the relative entropy. Which is the scaled Gibbs entropy. And the reason is that this is a convex and subadditive quantity. And so in particular, if I'm looking at marginals, right? So marginals is instead of looking at the joint law of the whole process, you're just looking at the joint law of the first k particles, right? So let's call them f and k. And they can be defined from Fn by integrating from the last n minus k variables. Right. And marginals, physicists sometimes also call them observables because those are the quantities that you can actually measure on the system, the statistical quantity, right? Fn1 is the one particle distribution. It's the expectation of the empirical measure that we had defined just before. Fn2 gives you some measure of correlations and so on. Then the relative entropy between the marginals, right? So this guy is directly bounded by the full relative entropy. So this behaves well. And that let us derive quite a few fun results. So 2D Navier-Stokes was the first quantitative derivation, and a variant of that is also when you combine it with some version of a modulated energy, you can get Kähler-Zeger. All right. And let me conclude this by describing very briefly a new idea that showed up very, very recently. And this is a way to work directly with the hierarchy when you have diffusion. And let me write this again for simplicity for first order system here, even though we really want to apply it to second order system down the line. And let me actually take a sigma that is independent of n. All right, so you have a hierarchy, which is the BBGKY hierarchy. On the marginals F and K. Right? And this you can get by taking the Liouville equation and integrating with respect to the last variables. Then what you have is the following. All right, in this, right, so in this term, everything depends on whether J is also going to be one of the first K variables or one of the later one, right? If it's one of the first K variable, everything integrates. And again, I'm still going to assume that K is divergence free here. You have this very simple expression. And otherwise, if it's one of the other variable, then they are all the same because of the symmetry of F and K. I'm looking at exchangeable systems here. And so what you have is this. But unfortunately, now this involves a next margin. And the diffusion is good. Okay, so this this is terrible, right? This second term here, right? And it's terrible for two reasons. You have a derivative, and you have a derivative not of f and k, but you have a derivative of f and k plus 1. And when trying to propagate norms on the hierarchy, this was essentially killing me. And it's killing you in the sense that if you try to do that directly in the hierarchy, you end up with an analytical norm. And you need analyticity not only of the solution, which of course you would never have, but also of the kernel. Right. So there are earlier works of Pulvianti when this is being done, and it's very, very hard to do anything else. Right? Clément had a result with Goltz and Ricci about some way of handling the hierarchy with only Lipschitz. But this was requiring already to be very, very clever. And it's not only a problem for Minty limits, it's because the hierarchy, you use it also a lot when trying to derive Boltzmann equation, and you have even worse of the difficulty. So this has been a recurring issue. But with diffusion, there is a very simple way around it. It had actually not been noticed, or maybe not really been used. I don't know. It's hard to say. But you have two recent preprints that make use of it. The first one in chronological order was a preprint by Dan Lacker. By recent, I mean last spring, by the way. And then we've also, actually it was more or less independent, we've also finished a paper with Soler and one of his former students on non-exchangeable system. We are also using something like this. And we are finishing a note with Bresch and Soler, which will use that to derive Vlasov Poisson Fokker Planck in 2D, and I think there's a lot of hope for 3D as well. So I think it's very, very useful. Now, Lacker was using the entropy, and this was using L2 norms. And I think the L2 version is a little bit easier, so let me explain it to you. Okay, so let me take the time derivative of the L2 norm. All right. And I forgot to write the divergence of K0. Okay, so because divergence of K0, right, this first term propagates every LP norm, so it doesn't show up. The second term here is, of course, going to be a pen in the neck, right? And it will look something like this after I integrate by parts. Right? And this, of course, would be the whole issue. If we had only that, it would be the end of it. But I have diffusion. Very, very well. And now I can do a very, so I have interval here. I can do a very simple Cauchy-Schwarz on the first term and the right-hand side, right? And this extra derivative that I would have no idea otherwise how to handle, I can absorb it into the diffusion. Then what I get is something like this. I'll get a 1 over sigma square. And then each term is rigorously the same, so that gives me an additional case n. I put n. So I get an extra k factor, right? And then I get this. Tx1, txk. And I can do an extra Cauchy-Schwarz here inside. And for that first order model, then I get that the d over dt of the L2 norm of a marginal of order k is controlled by the L2 norm of a marginal of order k plus 1, and they are constants, and those constants only require the kernel k to be in L2. And this is it. And now I have a hierarchy of those equations, and it works. The hierarchy actually works. So let's say that nk is this L2 norm. Then nk dot is lesser equal than some constant, okay, times k times nk plus 1. If the last one is reasonable, and we know it's reasonable because the Liouville equation behaves well, right? So if the last one behaves like constant to the power n, then this shows that nk actually behaves like constant to the power k. So you get an estimate, an independent estimate on every single one of them. There's also more than that, right? Because it only requires k in L2, nothing more. As a matter of fact, if instead of propagating an L2 norm, I'm propagating an LP norm, it only requires k in LQ with q the dual exponent. So I could go even lower than L2. And, well, what I've done on f and k, I can pretty much do on f and k minus f tensorized k time. Now there's an extra term, right? That's because f tensorized k times does not satisfy exactly the same hierarchy. All right, and in particular, it doesn't have those first term here, right? So this not here for f tensorized k times. So the extra term we have is actually of order k over n. But if f is smooth, that's okay. It's a very smooth term of order k over n, and you can do exactly the same thing. And if you do the same thing, what you get is that the difference. Right, so here I wrote it in L2 is of order k over n times some c to the power k. Now this with the relative entropy was what Lacker had done, right? We use this in a very different with Soler in a very different framework. But this is exactly what Lacker had done. Now with the entropy, you need k near infinity. But you have much better rate of convergence than anything that was known. Because you have convergence at order 1 over n and not 1 over square root of n, which was widely considered as the optimal convergence rate, and it is the optimal convergence rate for the relative entropy. This I can prove. But it's not the optimal convergence rate for the marginal. The optimal convergence rate for the marginal, as Lacker proved, is 1 over square root of n, is 1 over n, not 1 over square root of n. So this is really a relatively straightforward method, as you can see, but it's really fascinating. And as I said, we're actually finishing the first paper. This can be used to derive Vlasov-Poisson with diffusion. In dimension 2. Dimension 3 is a more complex case, so we need to work a little bit more. It seems to be working, but I'll be more careful, so I'm not going to write it down. At least the repulsive case. Right. Now, the key for Vlasov-Poisson is the diffusion is degenerate, but the derivative is also in V, so you can still play the same trick. Unfortunately, this proof is not going to work as is, because you also have to integrate not only with respect to the extraposition, but with respect to the extra velocity variable. And, well, you don't have compact support in velocity. So there are a few tricks here that you need to add to that to make it work for Vlasov-Poisson. But as you can see, this already gives you a relatively straightforward derivation of a mean-field limit for first-order system with very, very few assumptions on the interaction kernel, provided you have non-vanishing diffusion. This is it. This is essentially all I wanted to say. So thank you very much.
Yeah, thanks a lot. Thanks a lot. That's really interesting. Does anyone have any questions? I have. I guess even in the case of kinetic theory, your diffusion is only on the velocity variable.
Yes. Right? Yes.
And so already, I mean, is there some special structure that allows you to deal with this, or are you really building hyperellipticity into the entire scheme?
You don't even need that. It's really fun. So in the case of a kinetic case, right? What you would have here is you have gradient VI of f and k.
I see.
And here you would have gradient VI of f and k.
Right.
Here.
So I guess
you don't need to.
Yeah. So I guess this answers my next question, which is, well, no, it doesn't answer it yet. But I mean, so if you don't have sigma, positive on all the degrees of freedom, then
you need to have it. Yeah, you need to have it positive in the direction where you differentiate for this to work, right?
Is that obvious? Because if you had some hyperellipticity, then you could trade maybe regularity of k, something.
I don't know of any hyperelliptic result that would trade it 1 for 1.
What? Oh, trade it 1 for 1? No, you cannot trade it 1 for 1. Yeah.
And you would need to trade 1 for 1 for this to be working. Which is too bad, right? But Because of course I see what you're thinking of, and that's not going to work, not like that, right? It's still very remarkable that in the kinetic case, this the basic principle still is still good.
Mm-hmm.
The problem in the kinetic case, of course, and it's a very big problem, is you have something like this.
Yeah, I know what you're gonna say.
Okay, and you need to take the L2 or in general LP norm of that. And this is, if you keep it as is, it's not working. This would require a mixed norm, right? So you need LP in X, right, and L1 in V.
Yeah.
And those mixed norms are not propagated by the system at all, right? Kinetic equations are awful if you try to propagate something like this. So you need a few extra trick up your sleeve, right? Which I will keep the mystery on that for today, but maybe later in the semester I'll have time to go more into what we're actually doing. Okay.
Cool.
We use the energy, that much I can say, to resolve the problem.
Yeah, makes sense, I guess.
Yeah, and we use a reduced Gibbs measure and stuff like that. And the big difference between 2D and 3D is in 2D for Vlasov-Poisson, the Gibbs measure is actually integrable because you have exponential of a log, right? So you have a power law. And the inverse of the Gibbs measure is integrable as well. And in 3D, this is out of the question.
Interesting.
Yeah. I mean, it's fun that actually, I waited so long for a derivation of any derivation of Vlasov-Poisson with or without diffusion. And it turns out that the case with diffusion is actually relatively simple.
In hindsight.
Yes, in hindsight, which, okay.
A lot of work was required to understand, these limits.
I don't know. I mean, this is something that could have happened earlier, right?
It could have.
But it's interesting that you have two papers independently at the same time that are using the same trick.
Yeah, that's kind of odd. So are there any further questions? If someone has a question, they can just turn on their camera and ask it.
Or just put it in the chat.
Oh,
yeah.
I can't put on my camera, but anyhow.
Yes.
Thanks for your talks. Going back to your first talk, can you maybe say anything about the full parabolic Keter-Siegel mean field limit?
No, but that is an extremely good question. I don't know in the relative entropy method yet. I don't know how to introduce an interaction that is not instantaneous in time. Right. So for the full parabolic, so for other people, the full parabolic would be keeping the dt here, right, instead of throwing it away. If I keep that, even writing the Liouville equation is actually not easy. Because the value of the concentration, right, at a given time now doesn't depend only on the configuration of particles at that time, but also of what happened before. So you have memory effects in the linear equation. I was very fast on the relative entropy method. As I presented it, it was actually introduced by Yao in the 90s on the hydrodynamic limit for Ginzburg-Landau. But before that, you had a relative entropy method on trajectories, so on the full trajectories, right? So on the time-dependent curve that described the trajectory of the particles. And that had been introduced by Benarus. I'm not quite sure how to use that, and maybe that would be the better formulation if you want to go full parabolic here. That's sort of the best I can say.
Hey guys, sorry, I have to run, so you guys can keep discussing, but I'm going to be, I have to run, and then I'll see you guys tomorrow. Thanks again for the really nice lectures.
Thanks, Jacob. Bye. Sorry. So that's really all I can say. Again, the short answer is I really don't understand the mean field limit for the parabolic case.